All right, so we're going to go ahead and get started with the API section. My name is John Dagdelen, and I am a graduate student in the Pearson group. I've been in the group for about 5 years now. I started as an undergrad and then worked my way through and learned a lot about the materials project in PyMetGen, and now it's my pleasure to be here and share some of my knowledge with you all. Okay, so in this lesson, we're going to cover the materials project API, or as we call it, the MAPI, and its documentation, which is the Mappy Dock. We're going to look at getting our materials project API keys, which is available on our dashboard on the materials project website. We're going to use the materials project rester object, the MP rester, which is the PyMetGen object that allows us to connect to the database in a more functional way. And then we're going to do some hands-on examples through the exercises. So the first step, I want everybody to follow along with this. We're going to go to the materials project website and go to the dashboard. So let's go ahead and create a new browser window and go to materialsproject.org. And so you should be, since you've all logged into this site, you should log into the home screen or whatever you have set. Usually it's going to be this Materials Explorer app. And there's going to be a dashboard button right here in the top right corner. So go ahead and click that. And so right here in the middle, you should see this Generate API Key button, and you should see an API key here if you have one. And if not, it might be blank. Just go ahead and click this button, and then one should appear right here. This is your materials API key. This helps us keep track of the different users that are accessing data through our database, so we can make sure that the database is being accessed appropriately. So sometimes scripts can cause a lot of usage on our servers inadvertently, and so we use these API keys to kind of figure out, is it a specific one use of the API that's causing the load, or is it distributed across many users, and do we just need to scale? So this is just a way of us organizing that analytics, basically. So I want you to go ahead and copy your new key, and then there's going to be a line in your Jupyter notebook that says !PMG config --add PMG Mappy key, and then this caret your API key caret area here. So what I'd like you to do is copy your API key from here. Don't use mine, use your own, and paste it right here, and then run this cell. So I just want to make sure that this is working for everybody. Let me go ahead and pop open the chat, make sure everything's fine. So if anybody is having an issue, please go ahead and paste that in the chat, and then one of our helpers will pop in to see. Okay, so let's go ahead and talk about the Mappy Dock. So the Mappy Dock is our documentation for the API. It's kind of like a 1,000-foot view of what's available in the database. The database can be kind of complicated, and so this is a great way of accessing the documentation or seeing what is available in the database. So I'm going to click this link here. That same link should be available in. Let me just exit this view. So it should be available right here on the notebook that you see. And the Mappy Dock looks like this. So it's actually a GitHub repo. And the GitHub repo has this materials folder in it and some documentation as well about how to use the repo. But go ahead and go to the materials folder. And from here, the file structure or the folder structure of the Mappy Dock directly maps onto the structure of our database. So in our database, if you got the anonymous formula property of a materials project entry, that is going to have it's going to be a representation like this, and it's going to have the anonymous formula in the material. So for example, an anonymous formula might look like a dictionary with one key A, variable 1. So some of the properties that we're going to be using in this lesson, an important one is the structure. So let's scroll down to the S area. And so you can see structure here. So this is the structure property of materials project database entry. And we can see here that there are some sub-properties. Oh, I accidentally hit the spacebar. So there are some sub-properties here, such as charge, lattice, sites. So in your previous session, when you were building structures with PyMatGen, you could see this lattice, or you built the structure with a lattice property. And so that's exactly kind of how it maps into our database too. So a structure will have a lattice object, and then that has subproperties here. And so these example JSONs, or you can kind of think of these as Python dictionaries, that's going to be the structure in our database. So whenever you get stuck and you're not sure what key to look for, I want you to go to the Mappy Dock and go to materials, and then look through these properties here to see if they're what you want. And if you get stuck and you can't find the exact one you're wanting, you can always just search within the repository. So if you go to the Mappy Dock and you type search here, and so let's say I was interested in the structure, you can see in GitHub when you're searching, you can search in this repository. And so this is going to pull up all the examples of the place where structure was mentioned. So this is a good way of finding documents if they're buried a couple levels deep. You can use these, but they're not the best way to find it necessarily, because sometimes there's like 5 or 6 documents ahead of it. But we're working on better ways of documenting this. But that usually gets me what I'm looking for when I'm looking through here. Otherwise, I'll just go into materials and I'll just look for things that seem that they might be right. So if I'm looking for something like the lattice parameters, that's probably in structure. Or if I'm looking for the space group number, that's probably under space group. Or the crystal system, that's probably under space group. Okay, so let's go back to our Jupyter Notebook. Okay, so this next section, we're going to go through basic queries in the web browser. So I want to show you roughly what's going on behind the scenes when you actually use the MP rester. So our API is actually accessed through website addresses. So this is kind of how REST APIs work. These are called URIs, or resource identifiers. And so you can see here that we have our base materialsproject.org domain name. And then there's these extra kind of paths on this domain name. So you see REST v2. So this is our REST API version 2. And then we're going to actually look into materials. So that is exactly the structure of the Mappy Dock that we just saw, the materials folder. And then MP-1234. So this is the entry for the ID MP-1234. And then this last part is the VASP, or the calculation details we have for this one. So if you want to just put this in a web browser, and then you put your API key here as a parameter, you're going to see an output that kind of looks like, oh, maybe I didn't make this a subslide. You'll see an output that looks a lot like this. So this is actually a raw JSON document that you'll get in your web browser. And so this has all the information that I talked about in the Mappy. So let me just check Slack if there's anything here. All right. So this is not the ideal way to query our database, though. OK, so what I'd like to do is make some Pythonic ways of interacting with it. So one way you could do this is with the request library. So there's a nice library in Python called requests. And requests can make these calls to our web server and that get the data back from it, but it then puts it into a JSON object that we can then read. So for example, if we made this request, response equals request.get, we put in the same URL that we had before, and we specify our API key as a parameter to that function, then it will give us back something that looks like this. Oh, let me go ahead and paste my API key in here. And you will see that we get back exactly the document that we got from the browser, but it's in a Python document, or a Python object, which is nice to use. But again, this is kind of cumbersome because you need to know exactly the path that you're looking for the data you're trying to get, or maybe you're getting the entire document when you don't really want the entire document. You just want a single property. So let's look and see how we can do it better. So the way we do this is with what's called the MP rester. So the MP rester is a Python object. It's a Python class that's defined in PyMatGen. And the MP rester is going to be your main go-to way of accessing the database, OK? So in this section, this is going to start being where we get into the real deep part of the API section. We're going to be instantiating the MP rester, looking at its documentation, taking a little tour of some of the specialty methods it has, and just getting an overview of what the MP rester can do. And then we're going to do some exercises together. And then I'll have you all go off on your own and do an exercise where you use the MP rester for kind of a real task that you might do in a research project. And then we're going to come back together and go through a little bit more advanced ways of using the MP Rester, and then do a final exercise, which is a little bit more advanced. OK, so let's first talk about how do we start up an instance of the MP Rester. OK, so we should have had our MP Rester defined with this PMG config line. If that didn't work for you, I'd like you to go ahead and use your API key. So let's go ahead and instantiate the MP Rester. So MPR is going to be my variable name for the MP Rester is equal to MP Rester. And then you just paste your API key right here. One thing you'll need to do before you actually instantiate it is we need to import it from PyMatchen. So from PyMatchen, import MP Rester. And so if we run this, we shouldn't get any errors. Interesting. You might need to do from pymatchen.core. Oh, I just misspelled Rester. No problem. OK, so that should work. All right, so once we have the MP Rester imported, we can actually do some stuff with it. So let's take a look at the MP Rester and just hit tab after we have a period. And so you can actually see some of the functions that the MP Rester has with your autocomplete. It might look a little bit small on your screen. Let's see if I can do anything about that. No, it just seems to be defined by my browser. That's a little bit better, maybe. So we can take a look at some of these functions. So for example, we have get materials ID from task ID, get materials IDs, get stability, get reactions. So this is a huge, huge object with a lot of different functionality. So don't be too intimidated by not knowing what everything does all at once. We're going to use a couple of these functions to start with, and then we'll get a little bit deeper. So I'm going to move back down a little bit. So the first function I want to try running with you all is get supported properties. So if you start typing get, no. Sorry, it's not get supported properties, it's just supported properties. So that's where the autocomplete in Jupyter comes in very handy. That's why I always work in Jupyter, is because I don't always have everything memorized, and you probably won't ever either. And using this autocomplete really helps. So you can see here, if you print this, let me exit this view a little bit so you can see the whole list. So these are all the supported properties that you can query on in the Materials Project API. So this is a nice function to kind of look at the top level categories of the Mappy Dock too. Okay. So one thing though is that we recommend, if you want to make sure that your sessions are being closed properly. So this can be a problem when you're trying to run the MP Rester in a big script. So the with context manager in Python is a really nice way of making sure that this happens. So instead of doing mpr equals MP Rester, and then our API key goes in there, what you should probably do is with MP Rester as MPR, and then inside of this block, so we're indented here. Inside of this block, then you write your code. So mpr.supported properties. This is just a demonstration of this working. So the one thing is sometimes it might not print the same way in a Jupyter cell where you just have the object at the last line and it prints that thing. So sometimes you're going to have to do things like actually write print instead of just have it on your last line. So it works the same way. But if you then are outside of this cell, that connection will be closed. So that's a nice way of making sure that you don't end up with like timeouts and stuff like that. OK, so let's start using some of these MP Rester methods. OK, so this is sort of where we start getting interactive. What I'd like to do is try to get the band structure for this material MP1234. All right, so let me go ahead and I'm just going to pull this out. So we're going to go to the section right below this, and we're going to just get the band structure. Okay, so there should be a function in your notebook that has this. This is the code right here. So this function will plot the band structure for you. So what I want to do is just get a band structure and use this function get band structure by material ID, and then use this function to plot the band structure. Okay. So we're going to do this exercise together. And I want you to try to use the MP rester along with me in the with context manager and get a band structure. And then I'll show you that whatever variables you define inside the with context block actually persist. So these are variables that we create. So let's do this together. So with MP rester as MPR, colon. I'm hitting enter. It should auto tab for me. And let's call our band structure BS. That's our variable name. And we're going to do MPR dot, and then we're going to write the name of the function that we want to use. So the name of this function is get band structure by material ID. So get underscore band structure by material ID. And then if we shift tab, we should see the tooltip pop up that tells us what the input arguments are. So we can see here the input argument for this function is materials ID, or material ID, which is a string. So I'm going to go ahead and start a string using some quotes. And then I'm going to write the material ID, which is MP1234. And then I'm going to then exit the with context manager. So you can see here I'm on a new line that doesn't have a tab. And then I'm going to plot. I'm going to use the plot band structure function. And I'm just going to put our band structure in there. And before I run this cell, I need to run the cell above. I'm sorry, I didn't have you do that first. So now this should work. Now let's see. OK, so it connected the API, grabbed the data, put it down, and then plugged that into our plot band structure function, which looks like this. All right. So this is great. We were able to get data that is very useful to us. So if I have my favorite material and I want to get its band structure, but I don't want to go to the materials project website to get it, I can just plug it into PyMatch here and get it here. So maybe I wanted to do some analysis on lots of band structures. So I could throw this into a for loop for material ID, in IDs. So say I had a list of IDs that I wanted a band structure for. I could do band structure equals that and do some data on it. Process, yes, and then do that in a for loop, right? So you can do this many, many times and automate the process of whatever you wanted to do to a band structure object, for example, using a for loop. So that's something that we're going to do a little bit later in these exercises, okay? All right. So let's see. There's also a method to get the materials ID. So I don't always know the materials ID for what I'm working for. Usually as scientists, we think about things in terms of the formulas, right? Or the chemical system we're interested in. So there's a really nice PyMatGen function or the MP rester function for this called get materials IDs. So let's go ahead and use that and get some material IDs. Okay. So I'm going to do with MP rester as MPR. And then let's go ahead and get let's get a bunch of nitrides, for example. So let's say MPR, so nitrides. Actually, this is an exercise, so let's leave nitrides for now. Let's get all SiO2 structures. That's a more interesting thing. So SiO2 is equal to, we're going to get the IDs for these materials, not the structures. So MPR dot get materials IDs. And then we're going to put a chemical system in here, or a formula. So I can put SiO2. And then I'm going to print our SiO2 list. And so you can see here, this is the material ID for every single formula, or every single entry with the formula SiO2. So what if we wanted to expand this just beyond the SiO2 materials and just all materials in the silicon oxygen system? What we can do here, like you've seen probably on the website tour, you can put in a chemical system and get those materials. So this is just kind of the SiO system. Maybe I should rename it. So now we can see this list is a little bit wider. So that most materials in the SiO system kind of fall into this one. But we could do this maybe, let's look at the silicon nitride system. So there's fewer materials here, but we get that list. So this is a really neat, useful feature. So I will frequently start lots of my searches if I'm trying to search things in maybe the nitride family. I could just do a wildcard character here and get everything in that family. Star N. Maybe it doesn't work with wildcard characters here, but there's a function later that will. Okay, so let's use the API to achieve a research goal. So maybe so as a graduate student, maybe I'm going to a meeting and my advisor asked me to inspect the structure of this multi-ferric material and do something with it, maybe suggest some substrates for growing it. So what we can do is first get our structure for the material ID that we're interested in. And then let's go ahead and use the get substrates function to get substrates for growing that material. So I'll give you all a moment to think about this. And then I'm going to solve this with you. We do have some exercises that are more extended, and you're going to get about 10 to 15 minutes to solve those, okay? Okay, so let's go ahead and think about how we're going to solve this. So we probably want to start with our with context manager. So with MP-Rester, MPR. I need the parentheses here. So let's go ahead and get our structure. So start with structure is equal to mpr.get structure by material ID. And I'm going to go ahead and put my material ID here, MP-24932. And then now I need to get substrates. So I'm going to call it substrates is equal to mpr.get substrates. And then I'm not sure what the input to this is. So I'm going to hit Shift Tab on this, and it opens up the documentation or the doc string. And I can see here that it takes in the material ID. So I have my structure, and then I want to, instead of putting the structure in here, which we could try, but it would give us probably an error, we're going to put the material ID. So MP-24932. And then let's go ahead and print this list of substrates. Okay. So it looks like we got a warning that this calculation task is mapped to the canonical MPID. So this might have been a case where one of our MPIDs has been changed, we have a better calculation essentially. That is, so this old MPID is being mapped to this canonical one, which is this new 23501. So this is the MPID that we want to use in the future. So that's why we got this warning here. And so we can see here, now we have a list of substrates. So this is kind of hard to read, but it is a list of substrate objects that will help us identify which one we might want to use to grow it. So one way that we can make this a little bit more readable is put this inside of a for loop. So for s in substrates, print s. So this will do just a single line per substrate, which is a lot more readable. Okay. So at this point, So at this point, you should feel comfortable with finding the documentation on the MP-Rester. You should be able to create an instance of the MP-Rester and use methods from the MP-Rester. So what I'd like you to do, actually, sorry, that's for this next point. So now that we know that we can use these methods of the MP rester, I'm going to introduce you to a very important method of the MP rester, and it's called the query method. So the query method is kind of going to be your main working tool, I believe, with the Materials API. So let's go ahead and I'm going to just view it this way. So the MP rester query method gives us a lot of powerful tools to be able to basically directly query the database. So this is kind of what everybody tries to, or this is what everybody's really hoping to get access to through the rester. So this is what we're going to cover for the rest, pretty much the rest of this lesson, is how do we query the database? Instead of just getting one property at a time through a special method, can we do it in a general way? So the general structure of this uses the MongoDB query syntax. So this is something that you saw in the MongoDB part of the primer, if you attended that. But we'll cover a little bit of it here too, in case you weren't in the primer and you haven't seen MongoDB and you're not familiar. So the general structure of the way that we call the query is we have our MP rester instantiated instance. Then we use the .query method of that instance, and we give it two parameters. The first is the criteria, or these are what are we searching for, and then the properties are what properties of those entries should the rester return. So these are going to be, in this case, criteria is either going to be a string or a dictionary, and properties is going to be a list of strings. Okay. So let's go ahead and see how, let's learn how these queries work. So this first thing that we're going to do together is we're going to query for SiO2 compounds using the chemical formula through the pretty formula tag. Okay. So with MP rester as MPR, I put my parentheses in the wrong place. Sorry about that. Okay, with MP rester parentheses as MPR, let's go ahead and query for our SiO2 compounds. So let's call it SiO2 compounds. It's equal to mpr.query. And our first parameter, if we hit Shift Tab, you can see it's criteria. So let's go ahead and create a dictionary. And we're going to query for the pretty formula tag being equal to SiO2. So I'm going to write pretty formula. Pretty formula. And then I'm going to give it, since this is inside of a dictionary with the curly brackets here, maybe I can make my text a little bit bigger. Query, our first parameter is the dictionary, curly brackets. So this is the key. And then the value is going to be what we're searching for. So this is a string, SiO2. Okay. And then now we need to give it our second parameter, which is properties. And this is going to be a list. And let's just go ahead and get the MPID, so material ID. And then maybe we want to get the structure, so structure. So this should return a list of dictionaries where the key in the dictionary, the first, in each element has a key, material ID and a value of the material ID of the entry, and a key structure and the structure object of the entry. Let's see if we get that. So I'm going to, for S and SiO2 compounds, print S. And so you can see here, when this list prints, we get a dictionary. And this dictionary has a material ID key, and its value is MPI, or MP554665. It has a structure key, and the structure is a PyMatGen structure object. So we can do things like look at the length of this. And this will be, I might need to print this. Sorry about that. So we will see the number of entries that have been returned, which is 314. So we have 314 compounds, okay? And if we look at the first value, the first entry in this list, so I'm just going to evaluate SiO2 compounds bracket 0. So this gets me the first element in this list of SiO2 compounds. You can see here that the properties that are in this dictionary are exactly what we wrote in this properties list. So it only returns what we asked it to. We can also, if you're trying to do a basic query based on formula, composition, or stoichiometry, there's an easier way to do it, and it's actually the query method. And we can actually use the wildcard characters that I alluded to earlier. So let's go ahead and just try that out. So with mpRester as mpr, let's get the same SiO2 compounds. SiO2 compounds is equal to mpr.query. And let's just write SiO2 here for our properties, or for our criteria, I should say. And then our properties list, let's just get the MPIDs. Material ID. And then I'm going to print this. I'll just print the length of it. So we should see that same 314 come out of this search. And that's what we get. So let's say that I wanted to look for things that were maybe things that had oxygen in them, just any material with oxygen. So I could do star O. So this is going to give me all oxides. So these are simple oxides. These warnings can get kind of a little bit in the way of the lesson. So I'm going to run this cell here, which is going to get rid of my warnings. So if you want to run the same, you can. Let me scroll back down to where we were. Sorry about this. OK, so now we can see that we have 227 star O. So these are things with the formula like anything O1. So if we wanted to get stuff in the system of all oxides, so this is anything with oxygen, we can see here that we have 2,333. You also notice that there's this box that popped up, this progress bar. So the progress bar is actually a way of making sure that that you're getting your data without getting timeouts on your connection. So it's chunking the number of queries and data returned into pieces and then querying for them one at a time. So you get your full list at the end. But you're going to see a progress bar, and it's going to break up your query just a little bit. OK, so this is the time for the exercise 1. So I'm going to ask you to go into your notebooks. You should see on OCalc. You should see an exercise 1 notebook. So I'm going to go here, go into workshop, lessons, and materials API. And you should see Mappy exercise 1. So this is what you're going to see when you open your Jupyter notebook. I'd like you to go in. I have a typo here. Instead of structure, right here, this should be space group. OK? And I'm going to bold it just to double make sure. So get the space group property of the SiO2 compounds, not the structure. OK? So this should be, we're going to give you about maybe 10 minutes to solve this and then regroup. OK, in the interest of time, I'm going to go ahead and go over the solutions for this one. So if you didn't finish, that's OK, because just the first part was really getting the data. The second part was just plotting it. So to do this, roughly, we would use our MPR query, just query for the pretty formula as the first property, or as the criteria, get the space group object, and then iterate through that list of entries and extract the crystal system property out of that space group for each one. So this is a for loop where you just loop through the SiO2s and then add our crystal system to a list. And then we can count up the entries in that list to create some data that can go into our bar chart plot. And then you should get a bar chart that looks roughly like this. So we can see here that the orthorhombic crystal system is by far the most common one, followed by the tetragonal. And monoclinic is a third. So this is kind of a really useful way of seeing material science in a different way. So this is like kind of a materials project way of looking at things, where you can take a lot of data in aggregate. Rather than looking at one sample at a time, you can see, are there general trends for the overall, maybe an overall chemistry system, or across materials that have similar structures or things like that. So that's kind of a unique way that you can do science through the tools that the Materials Project provides that wouldn't be possible otherwise. Okay, so the rest of today, we're going to kind of look into a little bit more advanced MongoDB operators that you can use in your queries. And then I'm going to walk through the solution to the second exercise, which is not working on the CoCalc right now because it requires the structure matcher, which is not functioning at the moment. So unfortunately, we can't do that interactively with you all. I'm just going to walk through what you should expect from it. And then I encourage you to, at home or on Google Colab or in your own local Jupyter install, try to run try to do those exercises on your own. The exercise in exercise 2 is a very similar workflow to what I did in one of the papers that I published as an undergraduate. Okay, so MongoDB operators are really great because they let you do things like look for, is the value in a list? Or is it greater than a value I'm interested in? Or is it less than? So these operators all start with this $ inside of them. So the way we do it is we have our criteria dictionary, and we'll put the name of the field that we're interested in doing this query on. And then the value in this dictionary is not going to be a value like we did before, but it's actually going to be another dictionary. And the key to that dictionary is going to actually be one of these operators' names. So for example, if I wanted to look for materials with the energy above hull less than 0.25 EV, this is how I do it. I'd have the key be E above hull. I would have the property or the value be another dictionary, so I have more curly brackets. The key to that dictionary is going to be $ less than, or LT, $LT for less than, and then a colon, and then the value that needs to be less than, which is 0.25. Okay, so let's go ahead and do an example together. So there's this paper by Mikaneni et al. that proposes like a novel ammonia synthesis process based on some electrochemical cycling of lithium. And it's really interesting. So let's go ahead and use some of these MongoDB operators and ask the database for nitrides of alkali metals. So the way we're going to do this is we're going to look for cases where it has elements in the list of alkali metals and then has 2 elements. So these are basically simple nitrides. Okay. So let's start by just creating a list of alkali metals. So alkali metals is equal to, and I'm going to make this a list with a square bracket, and these are just going to be the element symbols. So we have lithium, Li, sodium, Na, potassium, which is K, Vidium, Rb, cesium, Cs. Okay. Now, let's go ahead and make our query. And I'm going to create, just to keep things clean, I'm going to create a couple other variables. So criteria is just going to be a variable here. And this is going to be our dictionary, where we're going to query on elements, but we're going to have to, the criteria be that the elements appear in this list of elements that we just wrote. So what this is going to do is say, if it has an element in this list, this is going to be a positive match. Okay. Moreover, this is going to be actually a compound one. So we're going to add a second thing to match against elements, because this is a dictionary. We can add a second entry in the dictionary. And we're going to require that all of the entries have an element that is equal to nitrogen. So this is going to be all. And then this one, you should put it into a list because it's the way it does matching. It needs it to be a list. So this is just an advanced example. Don't worry if you didn't know about all of these things right ahead of time. I'm just showing you what's possible. And then you're going to use the documentation of the MP Rester and the Mappy Dock to do these in the future. And then we're going to specify. So we're at this level of maybe I can do this. We're at this level. So now we're going to ask the number of elements to be 2. So this is an exact match. So we have this elements needs to have an element in this alkali metals list, and it needs to have nitrogen. And then it needs to be a binary compound. Okay. And so then our properties that we're interested in getting is a list. Let's just get the material ID and the pretty formula. Okay, and then now we can do our with MP rester as NPR, npr.query, and then we can just put our criteria and properties as these lists here. And then I'm just gonna print, I'm gonna use this short list function that was defined at the, oh, looks like I got a package. Sorry about that, everybody. I'm gonna use this short list function that I defined at the very top of the notebook just to make this readable. So you can see here that when we run this query, we get a bunch of binary nitrides. So 2 element things that contain nitrogen and a alkali metal. Okay, so this is kind of an example of some more advanced features that exist within this query method. It takes a little time to get a handle on it, so don't be worried if you don't fully grasp it just yet. It took me a little bit to get this, but I just wanted to give you a sense of what's possible here. Okay. There's actually kind of a bonus way of doing this. So this is a nice way of doing the same thing, actually. So I'm going to do short list. I'm going to delete this line. So I'm going to show you an alternate way of doing this using kind of the wildcard options. So short list npr.query. So if you remember, I told you that you can just put the chemical system here. You can actually specify with curly brackets the chemical system. So right here we have this. This is our criteria here. So this is going to give us all things that are in the chemical system of one of these and nitrogen. And then if I look for pretty formulas, our property list, we can see here we get a very similar list of compounds. So this is just an example. There's multiple ways of doing things in the rester. Just use the one that kind of makes sense to you. Okay. So in the interest of time, I'm going to skip this this last part here. There's a solution to it in the main notebook that's already filled out. But I'd like you to see this second exercise because this is an example of how we actually do material screening using the Materials Project API. Okay, so go ahead and open up your exercise 2 notebook. So that should look like files, exercise 2. So that should look like this. So this is not filled in yet. I'm going to open up the filled in one so you can see kind of how this looks. But let me walk you through what we're doing in this notebook before I do that. Okay. So this exercise covers a practical example of something that I did as a researcher in the Pearson group to find materials with exotic mechanical properties. So we kind of accidentally became aware of this material. It's a tetragonal polymorph of silicon dioxide called alpha cristobalite. It's a mineral. It has a really weird property in that it's one of the very few crystalline materials known to have a negative average Poisson's ratio. So that means that when you put tensile strain on it, it actually expands in volume rather than contracting, which is a really strange property because almost every single other crystalline material will get thinner along the opposite direction. And so we were interested in finding more materials with this property. And so the way we did it is we had a hypothesis that structure, the crystalline structure of this material was the key fact that made it have this property. And so we tried to find materials that had similar structure to this alpha cristobalite polymorph. So let me go to files and open up the solutions. So you don't have these solutions yet. I will post them, but I'd encourage you to try to give this a shot by yourself before you open up the solutions. That's why we didn't post them at the beginning so that you'd actually have to go through this. But we're running a little bit short on time. So I'm going to go ahead and just walk through the solution here. So actually, I'm going to run this on my own. Hold on. So I'm going to run this on my own browser so that I can actually run these cells for you so you see what's happening. Okay. Oh, it looks like I don't have the solutions here. Oops. Okay, let me walk through you on the CoCalc one. Sorry about this. I closed the window that had the solutions in them that I was interested in showing you. Okay. Okay, so the first step is to retrieve the structure of alpha cristobalite. So we do that using we can do the query. So we know that it has this, so if you only know its space group, you don't know its material ID, you're gonna need to find the material ID. And so one way that you can do that is just get all of the materials with the formula SiO2 and then kind of look through them for the right space group. Here I do a direct query on the database. So mpr.query, space group number equals 92. So I looked this up in the Mappy Dock, what the key I needed to find was. So that you can notice here, you can query on nested sub properties using this dot, the next part. So this is the main property. This is a sub property, okay? Then we search for the pretty formula being SiO2. So all materials, the space group 92, that has the pretty formula SiO2. And then I'm screening for stability based on this E above hull less than 0.1 EV, which is a good rough estimate for things that could be synthesized in the lab. Then we grab the structure that we queried for from this object, and we have our structure. This next section is what's breaking in CoCalc. We're instantiating what's called the structure matcher. And so this is an object from PyMatGen, which allows you to match whether two structures are the same or not. And if you give it loose tolerances, you can kind of build sort of a structure similarity comparison engine, which is what we do here. And then from that, we just test it out a little bit. We test it on the same structure. We're going to test it on a beta cristobalite structure, which is known to have a similar structure. So you should see that they match by this. And then you should see that just a random material does not match. And then finally, we get a set of candidate structures to compare. So in this one, the exercise here asks you to find all the vanadate compounds and then test them for structural similarity against the alpha cristobalite. So from this, we can just basically use we grab a list of vanidates by just doing our MPR query and giving it our anonymous vanadate formula, getting the materials ID, and then using that list of material IDs to find materials that have an ID in this list and are also stable and have fewer than 50 sites. Finally, we screen them against using our structure similarity against this vanadate compound, our alpha cristobalite against the vanadate compounds. And then it gets us a list of materials that have a negative Poisson's ratio. So in this case, I'm just printing out every single vanadate. And you can see here, actually, this is going to be the only one that pops out from that structure similarity. So I'm sorry that we couldn't run through this live with you all today, but please go ahead and give it a try on your own tomorrow once we have this issue fixed. And we'd be happy to continue answering questions on the CoCalc help chat on this notebook. And I'll be here tomorrow too, so I'll be able to answer questions on that so you can get a sense of it. So if there are any last minute questions, I'm happy to answer them now, but otherwise that concludes this the API use session. So what have we covered today? We covered the Materials Project API and the Mappy Dock. We found how to get our Materials Project API keys. We used the Materials Project Rester, MP Rester, to access the MP database, and we explored some hands-on examples of how to use the MP Rester and the API to screen the database for interesting materials. All right, thank you very much.